students William Harris and Woodamookli. Thank you for listening. Large language models, also known as LLMs, can use an internet crawl to utilize a large amount of data. The internet is also used to train LLMs. The relationship between the quality and quantity of content on the internet and performance of LLMs is discussed using a multimodal approach. The first area to discuss is the internet data defined as total dataset. Our approach was starting with dataset total, which simplifies the data on the internet as a sum of human-made, verified content and AI content. To further define HC, VS, and AI, we assume the population at time in accordance with the reference equation and graph shown. T in this model is taken from 2018. This is so the HC could be taken in 2018 as a total share of the internet. The verified source data stream, VS, is composed of three main elements: Wikipedia content, academic papers, and books. Each component grows exponentially with time, reflecting historical data trends in their respective domains. The verified sources also show a relationship between the verifiers at the time. The change in verifiers is assumed to be the same as the change in tertiary degrees produced worldwide, assumed to be 2.7% annually, and verifiers were set at researchers as 1.42 times 10 to the 3% of the population. Wikipedia content. This represents the cumulative informational content available from Wikipedia and similar curated platforms. The baseline size is 2018, denoted W0, is approximately 21 gigabytes. According to Wikimedia statistics, the annual growth rate RW is 15% per year, consistent with historical Wikipedia expansion between 2015 and 2022. Wikipedia contributes a smaller portion of verified data overall, so it is weighed by a factor of 0.2 in the total VS equation. Academic papers. This term represents the global flow of peer-reviewed research in formal academic publications. The baseline publication rate, A0, is 3 times 10 to the 6 papers per year in 2018, 2 megabytes each, and the annual growth rate, RA, is 4%, based on Dimensions AI and Scumdem datasets. Books. The baseline value, B0, is set to 2 times 10 to the books per year in 2018, derived from UNESCO publishing data. The average book size is 1 megabyte, and the annual growth rate is 2%. Generated content was defined as a fraction of total online content and calibrated against real-world data. The results show an explosive rise beginning with the introduction of ChatGPT, followed by gradual stabilization, with the midpoint of saturation projected around 2032. The dataset was validated using publicly available internet data. For simplicity, the model distinguishes only between AI-produced and human-produced content. It predicts that AI-generated content will eventually dominate the future, rendering the human-produced fraction negligible. The original equation incorporated variables for AI usability, hardware capability, and global internet availability. Usability is defined as a critical variable for AI-generated content. If an AI model is not usable, it cannot produce data. Usability, including accessibility, allows us to assume that across the variety of AI models, adoption will concentrate around the most usable systems. Therefore, the average usability of AI at any given time approximates that of the most usable model, or models of similar usability. The volume of AI-generated data is assumed to scale directly with available computing power, provided the usability remains at an adoptable level. Technological progress and processing power are simplified in the model as being proportional to hardware growth, represented by 4 to the T. Initially, the model was expected to saturate prematurely, approaching zero, due to database errors and the assumption that AI systems would not be able to effectively train on an open web with highly contaminated data. However, because both the maximum potential for AI content generation and the availability of large language models to crawl and utilize web data are functions of hardware, these effects cancel out in the model.
The relationship defined in this model between usability and error is that the higher the error generated by AI, the lower the usability. Error as used in this model is a simplified definition of a performance indicator. The human content error was expected by some sources on the internet to be around 50%, with no real evidence I could find. The error in validated sources could be assumed to be zero, however that is not realistic due to not all validated sources being 100% accurate. The relationship between usability and error was not approached as linear due to the error rates being relatively high and the models being usable. The usability is expected to experience exponential growth below a certain error threshold. When defining the AI error for this model, the simplified relationship between the dataset error and the correction factor produced change in AI error. The correction factor may be the most important part of this model. Rather, a lack of understanding on how a model is trained, the architecture of the model, and the resources needed to make an accurate modeling of a correction factor a challenge. The change in correction factor originated from the principle that verified sources are used to train LLMs. The relationship between AI-generated output and the amount of verified sources is not discussed in this model. The relationship would be the availability of unused verified sources and the error in the database and the hardware available over time. The effectiveness of the verified sources would decrease. The positive correction would be the processing ability of the hardware at the time multiplied by the change in AI workers, which was expected to be the same as the trend in computer science students worldwide, assumed to be around 8% growth per year with no real solid evidence. In addition, the change in the quality of the training process and model at the time, meaning the current used technology, the way this correction factor is applied had to be changed at this point of the model design. The model was chosen to attempt to reflect how multiple models created at different times could behave from correction and error data. When a new model is introduced, the previous model is no longer improved and continues to distribute AI data at that model's usability. The correction factor had to be defined in such a way that it works on consecutive models for only a short period, and then the change in correction factor over change in time becomes zero. A Heaviside function is shown, where the correction factor Ct is used and H is the hardware workers and model improvements. When changing H, or specifically the current technology variable associated with improvements in correction function, the model performance changes only slightly, increasing or reducing the trend of deterioration, meaning likely the use of OpenWeb is likely to be unusable for LLMs at some time t. The start of the mathematical model's training, the correction factor is at its highest for that cycle, but it is lowest overall. But it has the largest effect on the AI error due to the low error in the web database, so learning dominates and error decreases. AI-generated data begins to dominate. Dataset error rises, making the AI error and AI content term grow exponentially. Eventually, the learning term becomes too weak to offset the error term, causing the change in error over change in time to become positive, representing model degradation or collapse. This non-linear relationship captures the self-reinforcing feedback observed in modern AI training dynamics, where recycling AI outputs into future training leads to exponential degradation, as shown in the last reference. This feedback to the total database from the AI content and AI error produced had to be created, which then had to be modeled as a variable in the training of the model with a constant increasing difficulty of training for the LLMs. The AI error runaway could be modeled easily as a trend, but we wanted to produce a feedback that was dependent on how the LLM was trained at the time and its usability. The usability has E as the AI error and EM as the threshold that the model becomes usable. KU sets the steepness of the curve, and the exponential is shown to show the usability decreases exponentially as the error increases. The model did indicate some unexpected results, which we attempt to explain now. This model tends to suggest that AI models will collapse at some time t, reducing data produced onto the internet. If technology and processing power continues to improve, the future AI models at some time t will be able to produce a working model again, able to handle the level of error on the internet at that time until the model produces enough error data that the training models and the future models can no longer handle that error and begin the collapse again, indicating a cycle of growth and collapse. Improvements. To improve this model, simplifications of variables or more correct coefficients could be found. Also, a relationship between the quality of knowledge produced and quantity of knowledge produced with the use of highly usable AI could be a factor in the improvement of hardware. Thank you for taking time to listen to our presentation.